Good morning everyone, and welcome to today's worked exam answer video. Today I'm having a look at a Maxwell-Boltzmann distribution question, which for those of you in year 12 comes under the kinetics topic that you might have made a start on already, or you might be coming on to shortly after the half-term break. So in this question we are being asked to sketch the Maxwell-Boltzmann distribution of molecular energies for gaseous ethanoic anhydride at temperature T1 and then at a higher temperature T2. We also have to include a label for each of the axes. We have to mark on the appropriate axis as well a typical position for the activation energy, and then in terms of the explanation we're explaining why the rate of reaction is faster at T2. Now there's 5 marks for this, which is in my opinion quite generous. We don't often see Maxwell-Boltzmann distribution questions like this in the main body of an A-level paper, but this came from the 2023 A-level papers and it was the last question on the paper. Usually the kinetic stuff will come in for the multiple choice questions on paper 3. So there aren't loads of these from an A-level paper point of view. For those of you in year 12, lots of these will appear on AS papers, and clearly they do still come up on the A-level ones as well. Now in terms of the 2 temperatures, I've got my 2 colours for my lower temperature T1 and my higher temperature T2. I am going to draw the curves both in black pen because you will need to do that in your exam. For the purposes of showing you the differences between the curves, I'll then go over them in the blue and the red accordingly. So temperature T1 is going to be our lower temperature, so I'll go over that one in blue, and then the higher temperature T2, I'll go over that one in red. So when we plot Maxwell-Boltzmann distributions, we are plotting the number of molecules on the y-axis. You can say number of particles, but it's the distribution of molecular energy, so I think molecules is the better one of the 2 to use. And then the x-axis will always be energy. So we are plotting the distribution that shows how much energy the molecules have within a sample of a gas, and in this case the gas is ethanoic anhydride, which to those of you in year 12 won't mean anything right now, but for those of you in year 13 it will. It's an acid anhydride used in the production of aspirin. So that's our label on each axis done, so we can tick those off. We're going to mark on the appropriate axis a typical position for the activation energy. So by appropriate axis it means that it needs to be on the energy axis, so we're going to have to mark on the x-axis, not marking on the curves themselves, on the actual axis. So the activation energy, we usually find it somewhere over on the right hand side. We're not going to have the activation energy down here. The activation energy more often than not is higher than lower, and also if the activation energy was put there we'd need to show all of the molecules that don't have the activation energy, and we'd have barely any space to do that. Essentially not many of the molecules will have the activation energy, and in order to represent that we need to put the activation energy somewhere up here. So it doesn't matter exactly where because it's a sketch, but I'm going to mark it on there, and then I'm going to label that as activation energy, the E with the little subscript A there. And now we've got to think about sketching the distributions for the 2 different temperatures. Now we have to be really careful when we're sketching any Maxwell-Boltzmann distribution curve to make sure that first of all we start at 0, 0, because there are no molecules that have absolutely no energy at all. We don't want to then make it sort of like a bell curve. We need it to go steeply up at the beginning, and we need it to be skewed over to the left hand side. We also then don't want, when we bring the curve down here, we don't want it to touch the x-axis. We also don't want it to go down and then flick back up at the end, because that doesn't happen. Essentially, there are fewer and fewer molecules at higher and higher energies, but there is no infinite energy that the particles could potentially, or the molecules could potentially have. So we can't ever have that line touching the x-axis, which if you do maths, we can say that it's asymptotic. Don't worry if you've never heard that word before. So that's the first thing we need to do for temperature T1. And I'm a little bit nervous doing this live just because I don't feel I'm the best at drawing these, but here we go. So starting at 0, 0, not bad. So we're starting at 0, 0. We're not sort of coming up like that. We're going straight up, skewed to the left, and then we've got a decrease in the number of molecules that have those highest energies there. So that's my T1, and like I said, I'm going to go over that in the blue, just so that visually we can see. I would suggest labelling the two lines. It hasn't actually said label them, but I would definitely label them so that the examiner is clear, you know which one's which. Now, when we change the temperature of the gas molecules are going to have more energy. That's what higher temperatures do. Higher temperatures give the particles more energy. So we're not going to have the same shape of curve anymore. The shape of the curve is going to be different at different temperatures. However, all of the things that I just said still stand in terms of starting at 0, 0 and then having a kind of skewed curve. It won't be as skewed now, but it will still be a little bit skewed, and it will still come down towards the x-axis but never touch it. The other thing that's really important when we're changing the temperature is that we try to show that the area under the two curves is the same, because on a Maxwell-Boltzmann distribution, the area underneath that curve represents how many molecules we have in total. So if that represents 100 molecules, then my next curve will also need to represent 100 molecules, because changing the temperature does not change how many molecules there are. So what I'm going to need to do is try and keep the areas under the curve the same. Now, because it's at a higher temperature, the molecules are all going to have more energy than they did before. So the peak of the curve is going to shift to the right, and it also is going to come down when we increase the temperature. And the line that I draw for the higher temperature can only cross the line for the lower temperature once. And the bit sort of then on the left hand side, the size of that chunk needs to sort of match the size of the chunk that we gain on this side. You'll see what I mean in a second, hopefully. So this is where I then now have to think even harder than I did before, because I need to make sure that my areas under my curves are the same. I've seen worse, but I've also seen much better. But I don't think I'd be penalised any of the marks. I think some of that is just my need for it to look just right, which is not a realistic or sustainable approach. So I'm going to leave it as it is. So the curve in red there representing the higher temperature T2. So what we can see is the peak of the curve, which represents the most probable energy, is now higher than it was before. It shifted to the right. So if all the particles have gained more energy, then the most probable energy that those molecules or particles will have has to be a higher energy. There will be fewer molecules with that most probable energy though, and that's because more molecules will have higher energies, and that's why we're going to get an increased rate of reaction at T2, which I'll come back to in a second. My areas under my curves don't look too bad. And then the other feature, whilst I'm mentioning them, the peak of the curve is the most probable energy. The mean energy is always slightly to the right of the most probable. So mode, like in maths, is the kind of most common number. So when we're thinking about most probable energy, we're thinking about the mode. And mean, again, like in maths, if we added up all of the energies that all of the molecules had, divided it by how many molecules there were, we'd get the mean energy. And we find it's always slightly to the right of the most probable. Now, in terms of explaining why the rate of reaction is faster at T2, what determines how fast the rate of reaction is? Well, it's to do with how many molecules or particles have energy that is greater than or equal to the activation energy. Now, at T1, the only particles that had energy greater than or equal to the activation energy were those ones there. And based on how many sort of molecules there are altogether, not a very big amount of molecules have the energy needed for successful collisions, which is what is needed for a reaction to occur. When we increase the temperature to T2, we now have all of these extra molecules that have the activation energy. So it's all of these ones down here and all of those extra ones. Now, I don't feel that's massively representative of how increasing the temperature has a significant effect on the rate of reaction, because substantially more particles have the activation energy, and that's not really shown on the graph that I've sketched there, but you can still see that there are more particles that have energy greater than or equal to the activation energy. That means there will be more successful collisions per second, or a higher frequency of successful collisions. That means we are going to make more product in the same amount of time, and hence the rate of reaction will be faster. So for my final mark on this question, the rate of reaction is faster at T2 because more molecules have energy that is greater than or equal to the activation energy. Much quicker to do that than to write all of that out in words, which means more successful collisions per second, or a greater frequency of successful collisions. And there we have it. That's our Maxwell-Boltzmann distribution question for today. Any queries, please pop a comment underneath the video, or you can reach out to me via email at missgtutoringandresources@outlook.com. Thanks so much for watching, guys. I hope you're all keeping well, and I hope you all have a lovely half term when it comes. Take care.